curious. Okay, so I want to start today with a little mental exercise. I want you to just, picture a marble.
Yeah.
A standard glass marble. Maybe it's got a blue swirl in it, and it's just sitting there in the palm of your hand. You got it.
I am visualizing the marble.
Yeah.
All right. Now, I want you to scale that marble up. Compare the size of that little glass ball to the size of the entire planet Earth.
Right. That's a staggering difference. We're talking about a scale that is hard to even really comprehend.
It kind of breaks your brain a little, right?
Yeah.
But here's the hook. That ratio, the difference in size between that marble and our planet, is the exact same ratio as 1 nanometer to 1 meter.
And that really puts it into perspective. It really does. We throw around words like small or microscopic, but this is a realm that is so incredibly tiny, our normal intuitions just completely fail.
Exactly. When I say small, I'm thinking like a grain of rice, or maybe a dust mite if I'm feeling particularly scientific.
Sure.
But compared to the nanoscale, a dust mite is basically Godzilla.
That's actually a pretty accurate comparison.
So, welcome to the deep dive. Today, we are zooming in way, way into the world of nanotechnology. And I have to be honest, I see this word slapped on everything these days.
Oh, everywhere.
I saw a nanotech car wax, and I'm pretty sure it was just wax. So before we get into the really cool sci-fi stuff, we need to draw a hard line. What actually is it? Is it just anything that's small?
No, and that's a crucial distinction we have to make right off the bat because there's a lot of, marketing fluff out there. If you just make a transistor smaller, that's microtechnology. That's miniaturization.
That's just, honey, I shrunk the kids.
Exactly. It's impressive engineering, don't get me wrong, but it's still operating under the standard classical laws of physics. True nanotechnology is defined pretty strictly as the manipulation of matter, where at least one dimension is between 1 and 100 nanometers.
1 to 100. That seems like a very specific window. Almost arbitrary. Why not 200?
It's not arbitrary at all. That 1 to 100 nanometer range is the strike zone. It's the threshold where the rules of the game just fundamentally change. We're not just talking about smallness anymore. We are entering a regime where the laws of classical physics, gravity, inertia, all the things that govern our daily lives, they start to fade away.
And the weird stuff takes over.
And the weird, spooky laws of quantum mechanics take over.
And that is our mission for this deep dive. We're not just going to list small things. We're going to explore how manipulating individual atoms changes reality, how we figured out how to even do that, which is a crazy story in itself.
It really is.
And the huge tension between the medical miracles this promises and the potential environmental monsters we might be creating.
It is the ultimate double-edged sword story. But to really understand the stakes, you have to get the physics. You have to understand why that 100 nanometer line matters so much.
Okay, let's unpack the weirdness then. You said below 100 nanometers, the rules bend. The research we look at highlights two main sort of superpowers that emerge: surface area and quantum effects.
Right, and let's tackle surface area first. It sounds like boring high school geometry, I know.
I was going to say.
But at this scale, it's explosive.
I remember surface area to volume ratio from biology class, but refresh my memory. Why is this a superpower?
Okay, think of it this way. Imagine you have a solid cube of gold sitting on your desk. Most of the atoms in that block are stuck on the inside, right?
Right, they're surrounded.
They're surrounded by other gold atoms on all sides. They're stable, they're happy, and they're doing absolutely nothing.
They're the introvert atoms. They're staying home.
Precisely. But now imagine you chop that block in half. You've just exposed a whole new layer of atoms. Now, keep chopping and keep chopping down and down until you have a pile of nanoparticles.
Okay.
Suddenly, you have millions of these tiny particles, and a massive percentage of their atoms are now on the surface.
The introverts have been forced out onto the stage.
And they are not happy about it. This is the key. Surface atoms are chemically unsatisfied. They have what we call dangling bonds. They're missing neighbors, so they desperately want to grab onto something, anything to stabilize themselves.
So they just become super reactive.
Extremely reactive. You can take a material like gold, which is famous for being inert. It doesn't rust. It doesn't tarnish.
Right. It sits in shipwrecks for centuries.
Exactly. But if you chop it down to, say, 5 nanometers, it suddenly becomes an incredibly potent chemical catalyst. It can literally explode. It can make reactions happen that would never happen otherwise.
That is wild. So it's the exact same stuff, same element, but just by changing the geometry, just by making it smaller, you've turned it from a paperweight into a chemical engine.
You've got it. That's why nanoparticles are so useful for things like catalytic converters, but it's also why they're potentially toxic. They just interact with everything they touch.
Okay, so that's the chemistry side. But then there's the second factor you mentioned, quantum size effects. This is where you tell me gold isn't gold anymore.
It really isn't. And this is where your brain might hurt a little. In our world, the macro world, gold is yellow. Always. It's a defining characteristic.
Yeah.
But at the nanoscale, gold can be red. It can be purple, blue, even transparent.
Stop. How is that possible? I thought color was just a fundamental property of an element.
Well, color is just how light interacts with electrons. In a big block of gold, the electrons have plenty of room to roam around. They form what we call a sea of electrons.
Okay.
But when you shrink that gold down to a tiny nanoparticle, you're trapping those electrons in a very small box.
Yeah.
You're engaging in quantum confinement.
Like putting a wild horse in a closet?
That's a great analogy. And because they're confined, they start to vibrate in very specific ways. It's called surface plasmon resonance. The electrons oscillate at a frequency that depends entirely on the size of the particle.
So if you change the size of the particle,
You change the frequency of that vibration, which changes the color of light it absorbs and reflects.
so by shrinking the particle, you are literally tuning the electron.
You are tuning the fundamental properties of matter. Conductivity, its melting point, magnetism, all of these things we think of as fixed constants for an element are actually tunable variables if you can control the size of the cluster.
That is. It's like we've been painting with like 3 primary colors for all of human history, and suddenly we realize we can mix infinite shades just by changing the size of the brush.
That's a beautiful and very accurate analogy.
But here's the thing that always trips me up. We are talking about things that are a billionth of a meter. We can't see them. I can't just squint and see an atom. So how do we know any of this? How are we even having this conversation?
You're right, you can't see them. Not with light, anyway. The wavelength of visible light is roughly 400 to 700 nanometers. A nanoparticle might be 5 nanometers.
So the light wave is like a tidal wave going over a pebble. It just misses it completely.
Completely misses it. Your optical microscope, the kind you use in school, is useless here. To see the nanoscale, we had to invent a completely new way to interact with the world. We had to stop trying to look and start trying to touch.
The notes mention the STM, the scanning tunneling microscope.
Yes, this was the Galileo moment for nanotechnology. It was invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich back in 1981.
And how does it work if it's not using light?
Okay, think of an old school record player. You have a needle, a stylus, that traces the physical grooves of a record to create sound.
Okay, I'm with you. Physical contact.
Well, not quite contact. Imagine that needle is sharpened so perfectly that the tip is just one single atom wide.
Wow.
And instead of dragging it in a groove, you hover it just above the surface of the material you want to look at.
How close are we talking?
Incredibly close. So close that a quantum phenomenon happens. Electrons actually start to tunnel or jump across the tiny gap between the tip and the surface, and that creates a tiny electrical current.
So it's like a little spark jumping that gap.
A silent, invisible spark. And as you scan that tip across the surface, you measure that current. If the tip goes over an atom, the distance changes, the signal changes. If it goes over a hole between atoms, it changes again.
And a computer just draws a map from that data.
You're not taking a photo. You're drawing a topographic map based on feeling the electron clouds of the atoms.
That's amazing.
And it was revolutionary. Binnig and Rohrer won the Nobel Prize for it in 1986. But the real mind-blowing moment, the one that changed everything, happened a few years later in 1989.
What happened?
Scientists at IBM realized something else. They realized that if they cranked up the voltage on the tip just a little bit, they weren't just sensing the atoms.
You could do more than just sense them.
You could stick to them, they could pick them up.
You could literally drag and drop atoms.
They used the STM to pick up 35 individual xenon atoms and arrange them on a nickel surface to spell out IBM.
The world's smallest billboard.
But think about what that means. For the entire history of humanity, we've manipulated matter in bulk. We pour concrete, we smelt iron, we carve wood, trillions of atoms at a time.
Right.
This was the first time a human being reached down into the fabric of the universe and said, I want this specific atom to go here.
That is the moment it shifted from observation to construction.
Yeah.
That's the dawn of the era we're in right now.
It is. But what's interesting is, while the engineers were high-fiving over moving atoms, there was this massive intellectual war brewing in the theoretical world over whether we could ever actually build anything useful this way.
All right, let's go back in time a bit, because before IBM was playing Scrabble with atoms, there were people just dreaming about this. We have to talk about Feynman.
Richard Feynman, the rock star physicist. In 1959, he gave a talk at Caltech that is now legendary. It was called "There's Plenty of Room at the Bottom."
Such a great title.
It really is. And in that talk, he just posed a simple challenge. He asked, why can't we write the entire Encyclopedia Britannica on the head of a pin?
And he did the math.
He ran the math and said, look, the laws of physics don't forbid this. He argued that biological systems do it all the time with DNA, so why can't we? He basically called his shot 30 years before the tech even existed.
He saw the destination before anyone even had a map. But he didn't use the word nanotechnology, did he?
No. That word was coined later, in 1974, by a Japanese scientist named Norio Taniguchi. But the man who really blew this concept up in the public's mind and started the war I mentioned was K. Eric Drexler.
Right, the author of Engines of Creation.
Yes, published in 1986. Drexler was this incredible visionary, and he took Feynman's idea and just pushed it to its absolute logical extreme. He proposed the molecular assembler.
The replicator from Star Trek, essentially.
Pretty much. A nanoscale machine, a tiny little robot that could grab individual atoms and snap them together to build anything. A steak, a computer, you name it. He called it molecular manufacturing. He painted this picture of a world where scarcity didn't exist because we could just print whatever we needed, atom by atom.
And this is where the scientific community really split, isn't it?
Yeah.
Because that sounds amazing, but it also sounds, well, like magic.
It sounded exactly like magic to a lot of hardcore chemists, and the loudest, most prominent critic was a Nobel laureate named Richard Smalley.
The Drexler-Smalley debate. I love a good scientific beef.
Oh, this was a heavyweight fight. It played out in the pages of chemical and engineering news in the early 2000s. And Smalley argued that mechanosynthesis, this idea of building with little robot arms, was just flat out impossible.
What was his argument? Why can't we just snap atoms together like they're Legos?
He had two big points. The first was the fat fingers problem. He said, okay, if you build a robot arm to pick up an atom, the fingers of that arm are also made of atoms. They'd just be too big and clumsy to manipulate a single atom with any precision.
It's like trying to fix a wristwatch while wearing boxing gloves.
Perfect analogy. And his second point was the sticky fingers problem. At the nanoscale, gravity is meaningless, but stickiness, Van der Waals forces, is everything.
Right.
Smalley argued that if your little nanobot picked up an atom, it would never be able to let go. It would just stick to the manipulator arm.
So the robot would just get gummed up with atoms it couldn't release.
Right. Smalley's whole point was that chemistry doesn't work like mechanics. You can't force atoms together. You have to coax them with heat and pressure and solvents. He thought Drexler was selling pure science fiction.
That seems like a pretty devastating argument. Did Drexler have a comeback?
Drexler's comeback was simple. He said, look in the mirror.
Me.
You. Your body. You are proof that molecular machines work. Your body is filled with them. Ribosomes are these tiny machines that read a tape of RNA and assemble proteins one amino acid at a time.
So biology is already doing exactly what Smalley said was impossible.
Exactly. Drexler's whole point was, if nature can do it with soft, wet, squishy biological stuff, why can't we eventually figure out how to do it with hard, rigid engineering?
So who won the debate?
In the short term, Smalley won the PR war. Definitely. He convinced the funding agencies to focus on materials, science, better batteries, stronger coatings, rather than these far-out sci-fi robots.
So we got better khakis instead of infinite food. A bit of a letdown.
Maybe a little. But those materials, we really shouldn't scoff at them because, and this is the ironic part, while Smalley was arguing you couldn't build these cool new structures, his own team was discovering forms of carbon that completely changed the world.
We're talking about buckyballs.
Buckyballs. Buckminster fullerene, C60. In 1985, Smalley, along with Kroto and Curl, found this molecule that looks exactly like a soccer ball made of 60 carbon atoms. A perfectly stable, hollow cage.
And then after that came the nanotubes.
Yes, in 1991, Sumio Ejima discovered carbon nanotubes. Just imagine taking a sheet of chicken wire made of carbon atoms, that's graphene, and rolling it into a perfect, seamless tube.
And why are these little rolled-up tubes so important?
Because the carbon bond is one of the strongest in the universe. So these tubes are like tens of times stronger than steel at a fraction of the weight, and they can conduct electricity better than copper.
So this is where nanotech moved from, wouldn't it be cool if, to here's a bucket of actual stuff we can use.
Exactly. And that brings us to today, because I think there's this big misconception that nanotech is all future stuff. But looking at the research, it seems like I'm probably interacting with it right now.
Oh, you almost certainly are. We might not have Drexler's self-replicating assemblers yet, but we have absolutely mastered what we call passive nanomaterials. Nanotech is in your house.
Okay, give me the core. Where is it hiding?
Let's start in the bathroom. Sunscreen.
Sunscreen. Really?
Yeah. Do you remember that old school zinc nose coat? The thick white paste lifeguards used to wear?
Oh, yeah, the ghost look. Very distinctive.
That was zinc oxide or titanium dioxide. It was a thick white paste because the particles were big enough to reflect visible light. Today, your sunscreen uses the exact same stuff, but they're ground down into nanoparticles.
And because they're smaller.
They interact with light differently. They let visible light pass right through so the lotion's clear on your skin, but they still catch and block the dangerous UV rays. You get all the protection without the war paint.
That is a direct application of that size changes physics rule we were just talking about.
It is. Okay, now check your feet. Are you wearing athletic socks?
I am. And I assume they are now high-tech.
If they claim to be anti-odor or antimicrobial, they're likely infused with silver nanoparticles.
Why silver?
Well, silver has been known as an antimicrobial agent for centuries, but at the nanoscale, that surface area is huge. It constantly releases silver ions that just shred the cell walls of bacteria. So my socks are a chemical weapon against foot fungus.
Your socks are high-tech warfare.
Yeah.
I'll never look at my laundry the same way again. What about bigger tech? Cars, phones?
Electric vehicles are a huge one. A big part of the battery revolution is being driven by nanotech. They use carbon nanotubes to reinforce the battery structure. It basically prevents the battery from cracking as it charges and discharges over and over.
Which gives you more cycles and faster charging. Exactly. So the range anxiety you don't have is partly thanks to nanotubes. We also see it in sports equipment, lighter tennis rackets, stronger golf balls. But the field that I think is the most exciting by far isn't consumer goods. It's medicine.
This is where the source material mentions nanoencapsulation, and that sounds like a total game changer.
It is one of the most high-impact fields, nanomedicine. The concept of nanoencapsulation is basically building a tiny molecular delivery truck.
A truck for drugs.
Right. Think about traditional chemotherapy. It's brutal, right? It's essentially carpet bombing your entire body to kill a tumor.
It kills all the good stuff along with the bad. That's why people get so sick.
Exactly. Nanotech allows us to build a Trojan horse. We can encase the toxic drug inside a nanocarrier, and then we can cover that shell with proteins that are designed to only stick to cancer cells.
So it just floats past the heart, past the lungs, finds the tumor, and then it opens up.
Precisely. Targeted delivery, it reduces side effects massively because the poison only goes where it's needed.
And there was one specific example in the notes that just blew my mind. Something about cockroaches and DNA.
Yes, this is a fascinating study. Researchers used something called DNA origami to create nanobots.
I stopped on that one. DNA origami?
It's exactly what it sounds like. We think of DNA as the code of life, right? But physically, it's just a long molecule that pairs up in very predictable ways. I binds to T, C binds to G.
Okay, sure.
Scientists realized they could write a synthetic strand of DNA that when you put it in a test tube just folds itself up into a specific 3D shape. Like a tiny box.
Box made of DNA.
A box with a lid. And they designed it to have a molecular lock on that lid. The lock only opens when it bumps into a specific molecule found only in the target cells.
So they injected these into cockroaches.
And the nanobots successfully traveled through the cockroach's body, found the specific cells they were looking for. The lid popped open and they delivered their payload. It's a logic gate. If target is present, then open box.
That's computing inside a living creature.
We are performing computation inside a living organism using the building blocks of life itself.
It completely blurs the line between biology and engineering. We're using the stuff of life as a construction material to fix life.
It's profound. And speaking of computing, we can't ignore the electronics side. We all know Moore's law is slowing down because chips can't get much smaller using traditional silicon.
Right, we're hitting the physical limits of silicon atoms.
But nanotech offers a way forward. We're seeing things like on-chip optical quantum information processing using light instead of just electrons. Single nanowire lasers?
Transmitting information on a scale smaller than a virus.
Yeah. And just to show off what's possible, you have to mention the Nano Bible,
This was incredible.
a project by the Technion in Israel. They etched the entire Hebrew Bible, all 1.2 million letters, onto a silicon chip that is 0.5 square millimeters.
Half a millimeter. That's the size of a single grain of sugar.
It just demonstrates the immense density of information storage that's possible when you can control matter at this level. You could store all the data in the world in a shoebox.
Okay, so we have super batteries, cancer-fighting origami bots, and stain-proof pants. This sounds like a utopia.
Yeah.
But this is the deep dive, so we know there's always a flip side. We have to talk about the risks.
We do, and the risks are significant precisely because they stem from the exact same properties that make nanotech so useful.
The size.
The size. Small size means deep penetration.
That sounds ominous.
It's a toxicological unknown. Your body has defenses against dust, right? You cough it up, your nose filters it. But nanoparticles, they are small enough to slip right between the cells of your lungs and enter your bloodstream directly. They can cross the blood-brain barrier.
And that's supposed to be the fortress wall protecting our most vital organ.
And nanotech can just walk right through the cracks. Once they're inside, because they have that super high surface area we talked about, they are incredibly reactive.
Can you give me a specific, concrete example?
There is a famous and very worrying study about carbon nanotubes. Remember, these are the super strong tubes. But physically, they look like long, thin needles.
Okay.
And when they're inhaled, research suggests they behave in a way that is disturbingly similar to asbestos fibers.
Oh, wow. Asbestos. That is a loaded word.
It is, and the comparison is chilling. The immune system cells in your lungs, macrophages, they try to eat the fiber to clean it up, but the nanotube is too long and tough. The cell can't digest it, it gets frustrated, and it dies, releasing all these inflammatory chemicals.
And if that happens over and over again?
You get chronic inflammation, scarring, and potentially mesothelioma-like pathology.
So we might be manufacturing the next global health crisis in a lab right now and not even know it.
It is a valid and serious concern. We're creating materials that evolution just hasn't prepared our bodies to handle. And it's not just our health. What about the environment? Let's go back to those silver socks.
The fungus killers.
What happens when you put them in the laundry?
The silver.
Yeah.
It washes out. Into the water.
And eventually, it ends up at the wastewater treatment plant. Now, how do those plants work? They rely on colonies of good bacteria to break down our sewage.
Oh, I see where this is going.
If we flood that system with nanosilver, a powerful antibacterial agent, we could sterilize the very biological systems we rely on to keep our water clean.
So the very thing that makes the sock good, for me, makes it a potential disaster for the environment.
Precisely. It is the paradox of potency.
So who's regulating this? Please tell me someone is watching the store here.
Well, that's the regulatory gap. Agencies are trying, but they're mostly bolting on nanotech to existing laws. But the laws are based on chemical composition, not on size or structure.
Explain what you mean by that.
If you have a regulation for silver, it treats a silver coin and a silver nanoparticle the exact same way.
Yeah.
Chemically, they're both just ag, but physically, as we've learned, they act completely differently.
One sits in your pocket, the other penetrates your cell walls.
And the law doesn't really distinguish between them effectively yet. The notes mention that as of 2006, Berkeley, California, was the only city in the entire U.S. with specific nanotech regulations. We're catching up, but technology always moves faster than bureaucracy.
And that's the core dilemma, isn't it?
It is. If you regulate too hard and too early on a technology this new, you might stifle the very innovation that could cure cancer or solve our energy problems. But if you don't regulate enough, you risk an environmental or health disaster.
It's a tightrope walk over a canyon.
It is the definition of a transformative technology. Fire burns you, but it also cooks your food. Nanotech is the new fire.
So let's try to summarize this massive journey. We started with a marble in the earth. We went through the dreamers like Feynman, the fighters like Smalley. We're now literally wearing nanotech on our feet and putting it in our cars. But at the same time, we're standing on the edge of a potential toxicological cliff.
That is the reality of the nanoscale. It offers us these productive nanosystems, the ability to build from the bottom up. But it demands a level of foresight and responsibility we haven't really had to exercise before. We aren't just shaping wood or melting steel, we're rewriting the very code of matter itself.
It's fascinating and, yeah, a little bit terrifying, which is usually the sign of a truly big idea.
I agree completely.
Before we go, I want to leave our listeners with one final thought to mull over. We've talked about materials and we've talked about computing. But what happens when those two things merge completely?
You're talking about programmable matter.
Programmable matter. This was at the very end of the notes. Think about this. If we can control matter at the atomic level and we can integrate information science directly into materials, the line between hardware and software just disappears.
So you're imagining a physical object that you can update like an app, a chair that can reconfigure itself into a table, or a car body that can change its aerodynamic shape, or even its color on the fly.
We are so used to our phones changing with a software update. Are we ready for a world where the physical objects around us, our cars, our clothes, our homes, are just as fluid?
That is the ultimate promise of nanotechnology. It turns the physical world into a programmable medium.
Something to think about next time you put on those fancy socks. Thanks for diving deep with us.
A pleasure, as always.
We'll catch you on the next one.